Hey everyone, it's Nolan, and in this video I'll be doing an overview of avionics at Space Enterprise at Berkeley, and just for rocketry in general. So avionics is an integral part of rocketry, and really tends to get overlooked in the grand scheme of things. But without avionics, we can't really do anything. Avionics is the difference between a bunch of elaborately put together pieces of metal and a fully functioning rocket. So it really does make a big difference. So avionics is analogous to our nervous system. Right, we have a body made of bones and flesh and muscles, but without the nervous system, we can't really gain any information about the environment around us or take any actions to use our body to interact with the environment around us. And so similar to that, we can build all the mechanical aspects of a rocket, but without avionics, we can't understand how the system works or even get it to do anything, right? And so to get a good idea of what avionics is, I'll show you guys a little video. So it's not the best video, but I think it does a good job of getting the point across. Let's see. So this is a video of one of the hot fires we did. Pretty neat, right? And so as you're looking at this, the two questions are, one, how do we start the system? How do we start this hot fire without actually being near the system? How do we start it from all the way back here just by pressing buttons on our ground station? And the second question is, how are we getting data about the system in real time? So as you watch this flow occur, you'll see data coming in real time on these plots right here in these little boxes. And these are telling us what the system is doing. So the answer to those questions is avionics, and the rest of this video will be going into depth about how we do these things. So at a high level, avionics is really about two different things. One, reading data from sensors to understand the state of the system, and two, controlling actuators to alter the state of the system. And these two processes can be represented with these two flowcharts. So at the top we have a sensor on the system, which sends data to the microcontroller, which can be thought of as the brain of the system, which then sends it to our ground station where we can view the data in real time. Similarly, we have the ground station where we press a button to do something, and that sends a signal to the microcontroller, which then tells the actuator what to do, like opening a valve to start the flow. And we'll go into more detail about this process. One more thing I'd like to mention before we really get into it is that this video is in no way a comprehensive description of avionics, right? Some of these topics have entire university courses dedicated to them, so that would simply take too long. This video is more designed as an overview of what is going on in the context of the rocket, so that you know what questions to ask about how things work. So a very useful angle to approach the understanding of avionics is by looking at the flow of information from the sensor all the way to the ground station. So that's this top flow chart right here, and that's what we'll be focusing on. So we'll still be talking about how we actuate things, and this can still be understood in the same context as this pipeline of information from the sensor to the ground station. And so what you see here is an expanded version of this flow chart, right? We still have the sensor, we still have our microcontroller all the way to the ground station, and this is kind of what we'll be looking at, an expanded version of how data flows all the way from the sensor to the ground station. So when you're working with avionics, you'll inevitably be working with one of these subdisciplines, either on the system, doing PCBs, writing firmware, which is code, working on communications like radio or Ethernet, or coding the ground station. And then finally, we also store the data in a database so we could look at it afterwards. And so we'll be looking one by one at each of these processes to understand how data really goes from a sensor all the way to the ground station in our database. So the system is where it all starts, because after all, the system is what we're gathering data about. So it all starts at the sensor, where signals travel through wires, then to a connector where the signal enters the PCB, which we'll talk about later. And so let's get into how all of that works. So sensors are devices that measure some physical property and report it. And here you have the three sensors that are the most relevant to us and for rocketry in general. On the left is a pressure transducer, which measures pressure. In the middle is a load cell, which measures the force applied to it. And on the right is a thermocouple, which measures the pressure, or the temperature at the very end here and reports the temperature. And so most sensors operate on the same principle of outputting a voltage that is dependent on the physical property of interest. So for example, for pressure transducers in these wires, it'll output a voltage between 0 and 5 volts that can be interpreted as the pressure measured by the actual device. Same thing with the load cells and thermocouples. And so it's more important for us as the engineers to understand what to do with that voltage and how to interpret that voltage as the information we're interested in than it is to understand how the sensor actually works, right? Because we can just buy the sensor and it just works that way. It just outputs the voltage. We don't need it. We don't really need to. It's kind of abstracted away exactly how it does that. Nevertheless, it's still interesting to know. So I've attached some links for each of these sensors in the description about more detail about how they work and how they actually output the voltage. But again, like I said, the voltage that it outputs is what we're interested in. And what we do with that kind of forms the whole basis of avionics. So going back to this diagram, this entire pipeline is really just about transporting the outputted voltage of the sensor and digesting it into a format that we can understand and eventually visualize on the ground station, right? So the information really starts as this voltage outputted by the sensor, and then the entire pipeline is the process of changing that voltage and understanding it and digesting it into the format that we can understand and read and record for future use. Here's a picture of our combustion chamber after one of our hot fire burns. And the reason I like this picture is because you can actually see all three of those sensors in this frame. So see if you can spot them. On the top left here, you have two load cells. There's actually another pair on the right, which are kind of covered. But these load cells are measuring the thrust of the engine, right? So as the engine produces thrust down here, the entire force is being transferred through these load cells. And with that, we can measure the total thrust being produced. On the right, we have two pressure transducers, which are reading the pressures at the injector for both the oxidizer and the fuel. And at the bottom here are thermocouples along the entire combustion chamber. And these are reading the temperature on the outside of the chamber. And we're using those to make sure it doesn't get too hot during the burn. So the outputted signal voltages of the sensors ultimately need to be read by the microcontroller, which we'll get into in a bit, but for now you can think of it as kind of the brain of the system, where information is processed and sent to the ground station. And so that's what you see here in this picture. This is a picture of our engine testing cart, and you can see wires are traveling from various different parts of the cart, where there are sensors and actuators, and converging at the back here at the avionics box, where the PCBs are held with the microcontroller. So in addition to carrying signal voltages, the wires also carry power to the sensors that need it, as well as to the actuators to turn them on and off. So wiring may sound like a trivial discipline overall, but it quickly gets complicated when you have a lot of sensors and a lot of actuators, which you can see here. It's pretty crowded. And so doing proper labeling and proper cable management is actually definitely an important task. The simplest type of wire we use in this system is this 2-core wire, which is used to power actuators such as an electric motor and doesn't contain any information or data on it. Right? Both of these wires are purely used to supply power to the actuator. Similar to how fluids flow from areas of high pressure to low pressure, current flows from areas of high potential to low potential. So any power source, such as a battery, contains a high potential terminal, conventionally labeled with a plus, and a low potential terminal, which by convention is labeled with a minus. On the wire side, red wire denotes the high potential side, and black wire denotes the low potential side. These wires are both the same physically, they're just both copper, but we use these colors for convention and ease of understanding. So to power an actuator, you can think of the PCB in the avionics box as kind of a big battery that we can turn on and off. And so to power an actuator, we would connect one of these 2-core wires to the PCB on one side and the other side to the actuator. And once the circuit is opened, current flows out of that high potential terminal into the red wire through the actuator, and that's what powers the actuator, and then back to the PCB through that black wire. And so another way of denoting these two sides you'll see commonly is with power and ground. Power is always the high potential side, and ground is the low potential. So current will flow from power to the ground. Next is this 3-core wire, which is used by a lot of sensors, such as our pressure transducers. So in addition to the ground and power terminals, which are used to power the sensor, there is this third wire, which contains the signal voltage. And so the voltage of this wire, referenced to the same ground, is the voltage that we are trying to interpret as the information the sensor is reading. So some sensors use 4 wires, such as our load cells. So again, you have power and ground to power the sensor. And this time we have 2 wires for the signal voltage. So remember, a voltage is a potential difference between 2 points. So on this 3-core wire, the potential difference of the signal wire is between the signal wire and ground. But for these, we read the potential difference between the signal plus terminal and the signal minus terminal instead of ground. Oftentimes, sensors that use 4 wires will have an optional 5th wire for shielding. This is supposed to help decrease the amount of noise picked up by the signal wires in the surrounding atmosphere. Sometimes these signal wires will pick up on electromagnetic waves in the surrounding air that can affect the signal voltage and thus affect the reading that we get. So let's see what that looks like. Here's a plot of the load cell thrust readings during a hot fire burn. So before the burn starts, there should be no thrust reading, right? Should be at 0. Well, if I zoom in close enough, you'll see a bunch of these low amplitude fluctuations in the load cell values, and this is caused by just noise in the atmosphere, right? And so the shield wire is supposed to help decrease the amount of noise that these wires pick up on. An interesting exception for the sensors is the thermocouples, which actually don't even need an external power source to create a signal voltage. So this is the thermocouple wire, and it's actually a very particular type of wire where both of these cores are 2 different types of metal. And the 2 different types of metal will actually induce a voltage that is proportional to the temperature at this junction where they meet. And so the thermocouples don't need a power source. You can think of it as the 4-core wire of the load cells, but without the ground and power. And we can amplify this tiny voltage that's induced and interpret it as a temperature. So remember, all of those signal voltages eventually need to be read by the microcontroller on the printed circuit board on the flight computer. And so the way that these wires interface with the circuit board is with connectors. More specifically, we use these D-sub connectors to connect all of these signals as well as the power wires to the board. And so each of the pins on these D-sub connectors is connected to one of the wires. So for example, for one of those 3-core wires that we use for the PTs, there's going to be 3 pins on one of the D-sub connectors, one for ground, one for power, and one for the signal. And these connect to the other side, the other D-sub side on the PCB, which you see, which are these black things right here. So with this, we can transfer the signal voltage from the wires onto the board, and we can transfer the power from the board to the wires, which go to the system. Other connectors that we use more on the system side instead of for PCBs are these T-plug connectors. So these are for two core connections. So we use a lot of these for the actuators. And then we have these XT60 connectors, which we use for power on the board. If I go back to the PCB, you can see there's one right here. And this is actually where the battery connects to the board. And then we also use these 3-pin barrel connectors. So these are for forming connections with those 3-core wires. Okay, to recap what we've talked about so far, information starts at the sensor, right? The sensor outputs a signal voltage, and the whole point is to interpret this signal voltage as data. So this signal voltage travels through the wire into the PCB connector, those D-sub connectors, where it's going to enter the printed circuit board assembly. The essential idea of the PCB is that it takes in these various signal voltages and digests them into the language spoken by the microcontroller. So the voltages go through these application-specific integrated circuits, or ASICs, And these are just chips that take in analog voltages and output the digital signal read by the microcontroller. The other thing that the PCBs do is control channels to turn on and off the actuators. So in addition to taking in information and digesting it into digital information, the microcontroller on the PCB is also in charge of turning on and off channels that will supply actuators with power when we want. So first, a little bit of background on PCBs. Basically, when we're dealing with a lot of sensors and a lot of actuators, building up the supporting circuitry can quickly get very messy and very overcrowded when you're doing it manually or with breadboarding, which is what you see on the left here. And so a PCB essentially miniaturizes these circuits and allows you to fit more components and more wires in a much smaller amount of space. So instead of wires, what you have on a PCB are copper traces that are engraved on the surface of the PCB. And that's what you see here with these green lines, copper traces instead of wires. And instead of these components with legs and just a large overall profile, you have much smaller surface mounted components on the PCB that are directly mounted to the surface and allow you to fit way more components in a smaller amount of space. So like a resistor, which is what you see, these blue things right here, can get down to the size of a grain of sand on a PCB. So you can imagine how much more you can fit on something like this. The first step in designing a PCB is making symbolic schematics of all the subcircuits using tools like Altium or Eagle, which is what you see on the left here. Once the schematic is complete, the next step is to make a 2D layout of all the components and wires that you placed in the schematics. And for this, you're using the physical footprints of the components so that you know everything fits together. Once the layout is complete, you can print it into a printed circuit board, which is what you see right here. And so this contains all of the traces that you made in the layout and pads for all the components. The final step is to actually place all of your components by soldering them using a reflow oven. Hence, a printed circuit board assembly, right? It's an assembly because all of the components have been placed in their respective locations. Going back to the flow of information on the PCB, the main function being carried out is the conversion of these analog signal voltages into digital information. So a circuit that performs this conversion is called an analog to digital converter, or an ADC for short. And we use a lot of these ADCs. Basically, all of our data goes through an ADC at some point, right? Because it's starting off as a signal voltage and eventually becomes this digital format that the microcontroller can understand. So it's important to note that we don't actually design the circuits that perform these conversions, the ADC circuit. That process is abstracted away by chips that you can buy that do the conversion for you. And the circuits that we're designing are simple supporting circuits for the chip. So it's not as complex as you might think to design these PCBs, because a lot of the more complex parts are abstracted away by chips that you can buy, and then we just support those chips for our specific application. If you want to know how the ADC works, though, I've attached a link in the description that explains what's going on under the hood in these ADC chips. So what the ADC does is basically take a specific voltage range into its input. In our case, it's between 0 and 5 volts, and outputs a particular number of bits. So for the case of this example, I'm using 4 bits, but our ADCs actually have 16 bits. And so basically, if the input is at 0 volts, it'll output 0, 0, 0, 0, the smallest output possible, which maps to the number 0. And if the input is at the highest value possible, 5 volts, it'll output 1, 1, 1, 1, which is the largest number possible with this amount of bits, and that maps to the number 15. And basically, any voltage in between, it'll find the closest corresponding number using 4 bits. So for signal voltages with a very small range, such as for the load cells and the thermocouples, sometimes what we'll need to do is amplify the signal voltage to get within that 0 to 5 volt range for the ADC. So what you'll see is that this whole process is abstracted away by a separate chip, which contains both the amplifier circuit and the ADC circuit. And sometimes we'll have breakout boards that contain that chip as well as a supporting circuitry. So that's kind of the highest level of abstraction you'll get on these boards. And so what you'll see on this board is 2 load cell amp breakout boards. So in the middle there, you'll see the chip that has the amplifier and the ADC, and the breakout board itself contains the supporting resistors and capacitors and such. And so this is a breakout board that we really don't need to think too much about, and all we really need to do is give it the inputs and it gives us that digital output that will then go into the microcontroller. So these are very neat, and we'll see a lot of breakout boards, such as this one right next to it is also an ADC breakout board. So when I talk about the supporting circuit for these chips, that's the type of information that you'll find on the datasheet for the particular chip. So here's the link to the ADC that we use. This is where you can buy the chip on Texas Instruments, and you can see here there's a link to the datasheet. And the datasheet contains an immense amount of information about the chip, such as the underlying circuit, some descriptions of the various pins, the range of the input and output, things like that. And among them, you'll find the circuit that you need to support the chip. So even that is not really our design. Even that we're getting from the chip itself. So you'd be surprised how much of this is really just looking at data sheets and creating those circuits based off the designer's decisions. So learning to read data sheets is an incredibly useful skill for PCB design, because every chip that you use, you're going to have to look at the data sheet and determine if it works for your particular input or your output, what you're going to need to do to support the chip and have it work on the board. So another critical aspect of the PCBs is the power, right? All these different chips and subcircuits that we've been talking about need power in order to function. In addition, the sensors need power in order to output a signal voltage. And lastly, the actuators need power in order to do anything, like the motors need power in order to turn the ball valves, for example. So the way this works is that we have multiple voltage supplies on the board, and basically there's one high voltage input into the board in the form of a battery, and that's the only really power input into the board, and then we can step down that high voltage to lower voltage supply levels. And the way that works is by using particular chips that are made for stepping down the voltage level. So here you have an 8-volt buck converter, which takes in 24 volts and outputs 8 volts. Then we can use this lower 8-volt to step down to even lower levels like 5 volts and 3.3 volts. And these voltage levels are used mostly to support these chips and subcircuits, as well as for powering these sensors. And that's indicated here with the arrows leaving the board. So power stays on the board and supplies the circuits, but also leaves the board via those D-sub connectors we were talking about to power the sensors and the actuators. So at this point, our data has been converted from an analog signal voltage into binary, into ones and zeros that contain the information of this sensor output. So after this, all of these binary signals will converge at the microcontroller, which can be thought of as the brain of the system. This is like a mini computer that you can upload code to, which interacts with the pins of the microcontroller. So there are many microcontrollers out there. You might have heard of an Arduino. The one we use is a Teensy 4.1, very similar to the Arduino, but with more pins, a smaller overall profile, and a faster clock cycle. And so here's a picture of the Teensy 4.1 pinout. So this is a very important diagram that we look at a lot because the different pins have different functionalities. So it's important to make sure you're connecting the right traces to the right pins so as to not break anything or make sure you're getting the right capabilities. I've also attached a link in the description to the Teensy website, and this contains the diagram with a lot more information about what these pins do specifically and how the Teensy works. So in this picture, you can see the traces on this board converging at the microcontroller right here. So this is one of the layout diagrams of one of our flight computers. And you can see from various different parts of the board, the traces are exiting these chips and going towards the microcontroller, where it's sending the information to the chip where the processing will occur, and eventually the information will be sent to our ground station. And so that begs the question of how digital data moves throughout these traces in a way that's understood by the microcontroller, right? If it's just outputting a bunch of random ones and zeros, how does the microcontroller know when to stop reading the ones and zeros and interpret what it's been reading as a number and to move on to the next reading? And the answer is that there are many different communication protocols, which are just conventions using various different numbers of wires to communicate back and forth. And there's different communication protocols that have their pros and cons, and we'll briefly go over them, but in the description I've added more links that go into more depth about how these communication protocols work. So definitely check those out if you're interested. So the first of these communication protocols is called the SPI protocol, and as with all of these communication protocols, there's a master device, which in our case is always the Teensy, and then there's one or more slave devices which speak to the master device. And so this protocol uses 4 wires to communicate data. And so you can look at the link, more detail how this works. But what's important to know for now is that these two pins are used for transmitting the actual data. This is the clock pin, which kind of keeps the tempo of the communication. And this last one is called the chip select. And so this is where the master can choose which slave device it's going to be talking to. And here you can see how that would work for multiple slave devices, right? So all of the slave devices are connected to the same clock wire and the same data wires. And the only thing that's different is this chip select. So the master device has different pins for each different device. And by having one of these pins on at a time, it can choose which device it's talking to. And so on the Teensy pinout, you can see which pins can be used for the SPI protocol, and that's all of these, right? So these have the same labels that we've been looking at. And so if you want to use SPI, you would use these pins on the Teensy. So we're using a lot of these pins on the Teensy to talk to various different SPI devices, including our ADC, which speaks to the microcontroller over SPI. Here's an example of what that would look like in the actual layout. Here we have the ADC breakout board, and you can see it has the 4 SPI pins right here, MOSI, MISO, the clock, and the chip select. And you can see there's traces that connect to these pins and make their way to this connector, which connects to a separate board that contains the Teensy. So you can see how we use these traces to communicate over SPI. Another communication protocol that we use a lot is called I2C, or I2C. And this one's super useful because it only uses 2 wires as opposed to the 4 wires that SPI uses, or even more for that chip select for adding multiple devices. So like SPI, I2C has a master device, which is the microcontroller, and 1 or more slave devices, and all the data is being transmitted over this SDA wire, and this is the clock. So this is what it would look like with multiple devices. You can see each device is connected to the exact same 2 wires, and to determine which slave device the master wants to talk to, it'll send a particular address, and each of these devices listens for its address, and if it hears its address on the data line, it'll start sending its data on the data line as well. And so here's the pinout. You can see there are 3 I2C buses on the Teensy. Each of these pairs of SCL SDA is a separate I2C bus that can contain many devices, but if you want to have separate buses, that's always an option. And this is what it looks like in the layout. You can see this is the Teensy, and we have 2 pins, SCL SDA, and there are many devices connected to the same 2 pins. So up here you have a current monitoring chip that is connected to SCL SDA, and connected to the same pins you have this breakout board, which is an IMU breakout board, and these 2 chips right here. So note how all the wires, or all the devices, are connected to the same 2 wires, and that's pretty convenient because now the Teensy can speak to all these devices while only using 2 of the pins. The final communication protocol we use is called UART, and so this also uses 2 wires, but is specifically for communication between 2 devices. So this is different because there's no master device that speaks to multiple slave devices. This is just 2 devices that speak with a transmit pin and a receive pin. So one device transmits to the other device's receive pin and vice versa. You can see there's many RX-TX pins on the Teensy for communication with various devices. And so if we want to use UART for talking to a particular device, we can use any of these pairs of pins. Here's what it looks like in the layout. You can see there's 2 pins on the Teensy. These are surely one of those RX-TX pins, and it's actually exiting the board on this D sub first by traveling through these traces, and this is going to speak to an external device. Okay, so that's pretty much it for the PCB. Obviously, very high-level overview, but just to recap what we have so far, basically our data starts off as a voltage that is outputted by the sensor. It travels through the wires, enters the PCB via those D-sub connectors, where it goes through various different circuits that are mostly converting that analog voltage into digital information. and then it speaks to the microcontroller using these various different communication protocols. So at this point, our data has been communicated to those pins on the microcontroller using communication protocols, and it's in the format of ones and zeros that the microcontroller can understand as numbers. So while the microcontroller pins interact with our signal data, the microcontroller really isn't anything without the code that tells it what to do. And that code is called the firmware. The firmware tells the controller what to do with its pins and interprets the information and digests it into a format that we can understand on the ground station. So firmware is code that exists at the bridge between hardware and software, hence the name firmware. And so in the context of our data, the firmware is the bridge between the physical PCB and the physical signals and the software that is the ground station, where we can actually look at plots of the data. And so what do I mean by that? Well, similar to how you can set variables to true or false in Python, in the firmware you can set pins on the microcontroller to on or off, or high or low. So this is a line of code that sets pin number 13 to high, and all that means is setting that pin to a 3.3 voltage level. And so if you wanted to turn off the pin, you would do the same line of code, but with low, and that would simply cut off the power to the pin and leave it at 0 volts. So the other side of that is similar to the way you can check if variables are true or false in Python. In the firmware, you can check if pins are set to on or off. And so this is code that reads the state of pin number 2 and interprets it as either on or off, whether or not there's a voltage being applied to that pin, and then depending on the state, it'll print this text, hello world. And so these two functionalities are what allow those communication protocols we're talking about to work. For example, if the ADC was sending the number 15 as 1111 using one of those communication protocols, at every tick of the clock, it would make sure that that data line is set to a high voltage. And similarly on the microcontroller, every tick of the clock, the microcontroller will read the state of that data pin and interpret it as a 1 or a 0. And after 4 ticks of the clock, it can take the 4 numbers that it has recorded and form it and understand it as the number 15. So similarly, if it was trying to send 1010, instead of keeping that line on for all 4 ticks of the clock, it would first turn the line on, then off, then on, then off. And rapidly, the microcontroller is reading the state of that same pin and interpreting it as the number. So in the code, there's actually libraries that handle the complexities of those communication protocols. And you can see here we're including the SPI library and Wire, which is the I2C library. And so we don't have to really take care of the intricacies of, reading the pin at every tick of the clock. These libraries take care of that, and we can just use some functions of that library to use those communication protocols pretty efficiently. So the essential idea of the firmware is that of a constant loop that is executing over and over again while the microcontroller is on. And so here's a very simple example of that. So first you have a setup section that executes only once at the very beginning. And so here it's setting pin number 13 as an output pin. And then preceding that is the loop function. And so this is just going to keep running until someone interferes with it. And so what this is doing is just setting that pin 13 on and then waiting 1,000 milliseconds and then turning it off. So and then waiting another 1,000 milliseconds. So it's really just turning on and off this LED forever, essentially. And so our code is exactly like this, except there's more stuff going on in the loop, and we'll see exactly what we're doing in that constant loop. So one of the main functions of the firmware is to kind of determine what sensors to prioritize when reading all the different sensors. So looking at this diagram, you can think of each of these blocks as a different instance of that loop function. And what you'll see is that sometimes we'll read the same sensor, like the PTs, multiple times in a row before actually moving on to a different sensor. And so the reason we do this is because the pressures are kind of the data we're most interested in, so we want the highest resolution for pressures. And another thing you'll notice here is that some sensors take longer to read, longer to sample than others. Like the TCs take a bit longer than the PTs because the signal is going through the amplifier in addition to the ADC, whereas the PTs are just going through that ADC. And so to do this, we use what's called a scheduler to determine the frequency at which we're sampling each data point. So the firmware also dictates how each sensor is read, so exactly what is happening during one of these samples. So remember, in the case of our PTs, at this point, the microcontroller has received a number between 0 and 65,535 from the 16-bit ADC, right? And so this number doesn't really mean anything yet. And so what the code does is takes this number and does a simple interpolation to determine what pressure that corresponds to between 0 psi and 1,000 psi. And so this is the final step of that information being processed into the number that we're trying to understand about the physical system. And so each of the sensors kind of go through a different process, but the idea is the same thing of taking in that raw information into the microcontroller and processing it into the measurement, the final data that we understand as the physical characteristic. So the final thing that it does is it'll take this processed number and package it into what's called a packet. And so the packets are kind of units of data that are going to be transported to the ground station. So going back to our loop, sometimes the next thing in the queue will be an automation check. So one of the things our firmware contains is a logic for automated actions in case certain events occur. For example, sometimes we might abort a burn based off the temperature on the outside of the combustion chamber if it gets too hot. And so another example is automation that checks the pressure values in the propellant tanks. So if this automation check comes up, what it's going to do is going to check the previous few pressure samples and look at the values. And so here we see that if there's high values on average in the propellant tank, then it might be time to vent the tank because we don't want to overpressurize the tank. So it's going to check the previous values, and if the average is past a certain threshold, then it's going to execute an action such as opening a vent valve. And so this is something that happens automatically if the check is passed, as opposed to us sending a command to open the valve manually. On that note, sometimes the queue will get interrupted by a command received from the ground station. So that's when we manually press a button on the ground station to tell the firmware to do something. So there's two different types of commands. You'll get simple commands such as open the LOX vent valve. And so all this will do is open that valve. And what it's doing under the hood is just turning on the pin that corresponds to the vent valve. And turning on that pin will go through various circuits in the PCB and then supply power to the vent valve. Other types of commands are more extensive automation commands, such as begin ignition. And so this is a command that has multiple steps involved. So it's going to open these vent valves, close the vent valves, then open the pressure valve, start the igniter, and then open the main valve. So this is many events happening in a very particularly timed sequence. And this is an automated event sequence that can be triggered from a command from ground. Okay, so that's it for the firmware. Again, obviously a very high-level overview. If you want to look at the exact code, you can look at our GitHub under the firmware repository, and that contains the code that we actually upload to the PCBs. So just to recap the flow of information so far, the sensors are what take in the physical characteristic and output a voltage, a signal voltage, that then travels through the wires, enters the PCB through the PCB connector, which then goes through various different circuits to convert it from a analog signal voltage into a digital signal. And those signals speak to the microcontroller using those communication protocols. And the microcontroller is where the firmware is uploaded, and that dictates in what order the sensors are read, and it also takes in those raw digital values and converts them in the code into actual meaningful numbers, such as PSI values or temperature values. And then lastly, it's going to package those processed pieces of data into very particular packets, and those packets are going to be what's sent to the ground station using other communication channels, which we'll get into right now. So once the data has been packaged into these packets, they need to make their way to the ground station, right? Our computers, where we can actually view the data and send commands. And so that's the point of these communication channels. The first way we do this is with Ethernet. So you've all heard of Ethernet. Ethernet is similar to those other communication protocols we were talking about in the sense that data is being transmitted over several wires using ons and off on the wire. but Ethernet is made for more complex devices over much longer distances and is typically used to transport much larger amounts of information, right? Typically, Ethernet is used for network applications, so this is much more information than just simple a number being transmitted over SPI or I2C. And you can see there's dedicated pins for Ethernet on the Teensy, and you can see here the information is exiting the Teensy and makes its way to this Ethernet connector. And then here, this Ethernet cable connects to a network switch that all the different boards are connected to. And then we have a 300-foot Ethernet cable that leaves the system and makes its way all the way to our ground station. So you see this blue cable is a 300-foot long Ethernet cable that's traveling all the way from the system to our computers, where we can unpackage all the information coming from various different boards. And if you want to learn a bit more about how exactly Ethernet works, then I've attached a link in the description that goes into much more detail about the Ethernet protocol and how exactly it transmits information. The other way we communicate to the ground station from the rocket is with radio. When the rocket is flying, we can't use a 10-kilometer long Ethernet cable to transmit information, right? So instead, we use radio. And so radio is a way of transmitting information through the air using electromagnetic waves at a very particular frequency instead of through a wire using a direct current. So both on the ground station side and on the radio side, we have antennas that serve to radiate outward these electromagnetic waves and to pick up on them on the other side. And so we actually design our own antenna for the rocket so that it can fit this airframe, which is what these copper strips are right here, and that needs to be very specifically tuned to pick up on the right frequency and actually transmit and receive information. So that's what this process is showing. The receiving end of the communication channel is, of course, the ground station. So the ground station is a software built with JavaScript for the dynamic elements and CSS for the more visual elements, all within the React framework for the UI. And this is basically run on our computers so that it can display the data that's being received by the computer and also send commands back through the communication channel to the firmware when we want the system to do something. So this is a little bit outdated, but you get the general idea with this. And this is a screenshot of the data window, which portrays all the data that's being received. And here on the bottom left, you can see live thermocouple data coming from the engine. And all of these other boxes are displaying voltages and amperages of various points in the on the PCBs. The other side of it is the control window. So these contain a lot of buttons where we actually input commands such as opening valves or opening or starting the flow, things like that. And so what happens is we press buttons and then it'll send a command back to the firmware through the communication channel. So these diagrams depict the underlying processes going on with the ground station. On the left here we have the data side of things. So for the data, we receive a packet of data through the communication channel by reading one of the ports on the computers. So if we're communicating over Ethernet, it'll read the packets from the Ethernet port, and if we're communicating over radio, it'll read it from one of the USB ports, and that's just how the radio module communicates with the computer. So what happens is we unpackage the packet, and then the first thing it does is check the packet using what's called the checksum to make sure the data hasn't been corrupted, and then once that passes, it'll take the information out of the packet and send it to the right plot to be visually plotted using visual CSS elements. And then what's also happening is the data is being recorded to a local influx database, which we'll get into in a second. The other side of things is the command side. So it's kind of the reverse of this. We have buttons that are coded using software buttons that are coded. And what happens when we press the button is dictated in JavaScript, and it's going to basically package a particular packet based on which button has been pressed that is then sent back out through the communication channel by sending it to that port on the computer, and that'll be received in the firmware later on. It's arguably more important to look at the data after the fact than it is in real time, hence the importance of storing the data in a database. So like I mentioned, the ground station records the data in a local influx database that we then upload to a server, and that's where we hold all of our data basically for any of the flows we do. So this is Chronograph, and Chronograph is a tool for visualizing the Influx data. So it connects to an Influx database and allows you to create dashboards and visualize the data that's stored in that database. So whereas Influx is the database, Chronograph is a tool for visualizing it. And here you can see we have a list of all the different dashboards for different tests that we've done. And if you click on them and go to the proper time frame, you'll get something that looks like this. So this is different cells portraying different pieces of data, and you can configure what data it's portraying with these queries, and these queries are very similar to SQL queries. And yeah, you just type in a query, press submit, and then visualize different pieces of data. So you have a lot of freedom as to how you portray this data. We could put everything on one plot if we wanted to, but obviously we don't want to do that. And there's also different ways of looking at the data, such as with a table instead of a plot, things like that. So this is definitely an important tool that we're using a lot, especially after a flow is complete, to review the data and make sure everything looks as we expect it to. And with that, that's pretty much it. So definitely good job if you made it this far. I know it's been a really long video, but there's a lot that goes into avionics, so it's hard to really fit it into a compact form. I think understanding this whole pipeline from a high level, or having a working understanding of the flow of information from the sensor to the database and the ground station, is pretty critical for understanding avionics as a whole, because most of what we do happens somewhere along this pipeline, right? So kind of understanding the high level context of the thing that you're working on makes it just more meaningful to work on and easier to understand why it is you're doing the thing and what exactly the purpose is in the bigger picture, right? So with that, thank you for watching this video. I really hope you learned something new, and as always, remember to ask questions, right? This video is designed not as a comprehensive deep dive, and so with this, you should be able to understand what questions to ask to learn more about these specific steps. And remember, asking questions, there's no such thing as a bad question, so asking questions is critically important to expanding your overall knowledge of such a complex topic as rocketry, and especially the avionics going into rocketry. So with that, that's all I have, and I hope you enjoyed. Thank you.